Okay, so we have a question submitted in about doing chain rule when involving more than just two functions. So the whole thing to chain rule, and this is where it gets its name, is that there really is no limit to the amount of times or amount of functions that you can have when you're doing chain rule. You just keep deriving until you've reached and derived the innermost function. So we'll take this as an example here of that occurring. So if we look at this, and I'm going to circle here in different colors, are functions that we're dealing with. So we have really there is this square root that we have that we can consider our first function. So I'm going to call this f. Then inside of that radical, you have this other function here, and I will use a different color for that. So there's this. And inside of that one, there is yet another function, which is, oh, there's this square root here. Oops. So there's this other function there, and then inside of that there's this other one in here, and then you have that. So we really have quite a few functions, one nested inside the other. So just to make it easier to see, and we have discussed this in class, is sometimes it's just better to write this instead of looking at it in this radical notation. Let's look at it as if it were written in the fractional power notation. So I'm going to do that. So 2 plus, and then there's this 2 plus, and then this was x to the 1/2. This was to the 1/2, and this is to the 1/2. So in this way, I really see this chain rule starting to form. So now let me go ahead and start writing it over here. So the first thing I see is, well, this is my outer function, this square root, so the one that I had circled originally. Okay, so how do I do that? Well, that would just be 1/2 the function to the negative 1/2. Well, what was inside is what I, again, write here. So this would be that 2 plus x to the 1/2, and all that sorry, was to the 1/2. So 2 plus, and then all this was to the 1/2, like so. Now I'm going to focus on, and I'm going to highlight it here. So now I got to derive is this thing. Well, there's an addition that's happening here. So deriving the 2, that would be 0. So I'm going to write the 0 out just so you can see that. So 0 plus, and now, oh, I got to derive this. But to derive this is chain rule. Okay. So let's do that. So this would say 1/2, 2 plus x to the 1/2 to the negative 1/2. So I've derived was this function, this x to the 1/2. Now I have to continue deriving because I'm not to the innermost function. Now I'm getting there. You see, now I get to this part here. So this, okay, I'm going to derive. So again, another multiplication. So now here, again, it's an addition. So derivative of 2 is 0. And the derivative of x to the 1/2 would be 1/2 x to the negative 1/2. So now I've derived that innermost function. So I've gotten to the core of this composite function, and I've derived that core. So that means I stop at this point. I don't keep going now again. So this would be it. Now again, it's all in fractional notation, which is fine. If I wanted to simplify this, I would just get rid of these 0 pluses because they don't do anything to the ultimate answer at the end. So let me just clean this up a little bit here. This is the negative 1/2 times And then we had 1/2 times, and then 1/2 x to negative 1/2. And again, you don't have to worry about simplifying this. I could just leave it like this. Obviously, there is multiplication that I could do. I see I have a half here, times there's another half that's here, times another half that's here. So you can clean this up if necessary, but again, in this case, it's not really necessary to do so. Now, one trick that you can do for this is, and this now involves, so we just finished discussing implicit differentiation. So this is one where the way that this is written really makes it hard, or not hard, but just makes it really difficult and a little bit more time consuming to like keep track, because I see this repetitive nature of what the function is doing. So what you could do is to maybe implicitly derive it. And here's what I mean. I'm going to make the explicit implicit. So one neat technique you can do is, when you start getting crazy stuff like this with radicals, is let me rewrite it. So why don't I just square both sides? That gets rid of some of the radical that I have to derive, so that I can do, oh, okay, I'll just add the, or subtract the 2, sorry, to the other side. So now you start seeing, oh, now there's less radicals, so it's not too bad. I could, now I'll square this side again. So you see, I'm trading like my radicals for squareds. So now I got 2 plus square root of x. Now I'm going to stop here. I can keep going. I'll move the 2 over and then I square it. But then it's like, okay, you don't have radicals, but I'm still kind of then having to deal with a lot of nested functions. I would stop here. And now I would say, okay, let me derive that. So now implicitly, I could, this isn't too bad to derive. So I would say, okay, 2y squared minus 2 times the derivative of the inside, which would be 2y dy dx, equals, and then on the other side, it would be 0 plus 1/2 x to the negative 1/2. Okay, again, I want to isolate that dy dx. So this is just multiplying over here. So all this is multiplying. Let me circle that. So all this is just multiplication. So we'll just divide it over here to the other side. So dy dx equals, and that would have had 1/2 x to the negative 1/2 over 2 y squared minus 2 times 2y. So just to, again, clean this up a little bit, so you have 1 over, and this would go to the bottom, so you would have 1 over 2 times 2 times 2, which is 8. And then you're going to have that y times y squared minus 2. And then this x to the negative 1/2 really would be down here, x to the 1/2. So this, you see here, is a lot cleaner to look at, but it would be what we ended up writing here. Like if I really want to show how this is equivalent to what we just finished doing. So remember, I didn't bother to multiply those 1/2s, but had I done that 1/2 times 1/2 times 1/2, there's that 1/8 showing up. Well, what's y? So originally y was that radical, which you're seeing here, x to the negative 1/2. So that's showing up here. There's your x to the 1/2 down here in the denominator. That y squared minus 2 would be then this portion here. So you see how, or hopefully, I'm hoping you see how sometimes doing it implicitly would offer an easier avenue, especially in a case like this with nested functions. But just so you do understand, it doesn't matter how many functions you have. Let's say if I do something like this, it doesn't matter how many functions you have. When you derive, you just start deriving from the outermost function, and you just start building your way by deriving it piece at a time, like so, until you've gotten to that innermost function and derived it. So you don't stop till you derive that innermost function. Once you've done that, then you're good. And that would be the derivative. So chain rule, that's why it gets its name. You continue to chain derivative after derivative after derivative till you've gotten to that innermost function.